Alright guys, sorry I can't be with you again today, but I will be there with you on next week, hopefully. And a couple of things I want you to pay attention to are on the slide. Please pay attention to announcements on Canvas. Every week I have an announcement coming out, but also other announcements come out periodically. Start studying for test number 2. The test guide is posted. Some of you told me you did not look at the last test guide. It's very important that you look at it ASAP before you come to class next time. There's something important on there. For Friday is your quiz number 4. Again, you can use your spectroscopy handout. One thing that's not on your spectroscopy handout is triple bonds, the hydrogen on a C, on the carbon on a triple bond, the sp. Those are a little bit more upfield than like an alkene. So that's something that some of you may have noticed from your textbook, and I just wanted to say that. You can add it to your handout if you'd like. So we are going to continue with our worksheets. So we actually finished up some stereochemistry. We started substitution, and hopefully you finished up your substitution on your last worksheet. Again, to be successful, you got to practice, practice, practice. As you're working on your worksheet, Dr. Shelby will call different groups up to the board to do different parts of the worksheet up to a certain point. So after you finish watching this and you've moved on to page 10 of your worksheet, you're going, group 1 is going to be asked to draw the rearrangement, so pay attention to the questions on Canvas to kind of help you. On page 11, group 2 will be asked to write the rate equation on the board for elimination for E1. Group 3, you're going to, on page 3, there's going to be some little diagram about sterics and nucleophilicity. You're going to state out loud what's the trend that you observed. Group number 4, you're going to be asked to draw cations, the cation and the leaving group for a certain reaction on page 12. You don't need to write this down now, it will come back up. And this will also be here on Canvas. Group number 5, you're going to be asked to draw some mechanisms. Group number 14, you're going to be asked to draw explain something from question number 45, and then the rest of the worksheet you just need to be done with. You can work with your groups for the whole thing, but you need to submit individually. If you don't submit, you're not going to get a grade. So we don't have any clicker questions because I'm not there for you to do your clickers, but here's a clicker question, and here's how to kind of help you go through this. So this is from the last class, as well as normally I would have done this on Tuesday, so that's why it says reading. So here's a question that's asking you to figure out which one of these mechanisms are concerted. So these are all substitution, because if you notice, we're replacing the chlorine with something else. And since it says concerted, it's SN2. SN2 means that there's only one step. So for this reaction, we're looking at substitution in an SN2 fashion. And if we look through all the mechanisms, this mechanism has the leaving group leaving first. So that would be wrong. This one has the nucleophile coming in, but the leaving group isn't leaving, which can't happen. And then over here, you have your nucleophile attacking your electrophilic center, kicking the leaving group out, and that is an SN2. So this is good for type of stuff for you to practice. All right, so for today, we are going to be working on our worksheet. We'll do a spectroscopy problem next time. We will work through some of the problems for the substitution elimination part of your worksheet. So you'll finish the next 2 pages of your worksheet and then move on to the handout from Dr. Shelby. So we're going to continue with our learning objectives, which includes E2 and E1 today. There's a couple of stuff related to SN1 and SN2 as well, so that's coming up. Last class, you had to rank things according to ARIO in terms of nucleophilicity and electrophilicity and leaving group. The same thing occurs with bases, except size matters with bases, and then also draw mechanisms. So our molecule of the week was doxorubicin, and we're going to talk about an application of doxorubicin to what we've been learning. So you can go back if you want to remind yourself from last classwork what doxorubicin is if you'd like. But here is a practice problem for us, and we talked about this in class. So whenever you have OHs and NHs on a molecule, on NMR, sometimes they're a little bit confusing, so we can do something to make them show up, which was called the D2O shake. So what we're going to do here is identify all the groups that will disappear with a D2O shake. So remember, all of those are NHs and OHs and nothing else. So I'm going to look for my molecule and I see an OH. So if I did a D2O shake, that hydrogen should disappear. I have another OH. And then I have another alcohol, so all of these are alcohols, and then another alcohol, so I have 4 alcohols that will disappear with a D2O shake. And then I have an NH2, so, oh, there's one more, so it's 5 alcohols and 1 amino. So this is a primary amine. All right, so for substitution elimination, one thing that's not on your worksheet that I want to talk about is the fact that we talked about HOMO and LUMO at the beginning of the semester. HOMO is the highest occupied molecular orbital, which means that they have electrons, and LUMO says lowest unoccupied, so they don't have electrons. So when we think about nucleophiles, we're talking about things that have electrons. And so when we think about where those electrons are coming from on the nucleophile, they're coming from the HOMO of that molecule. And when we think of the electrophile, since it lacks electrons, we're talking about its LUMO. So pretty much what happens is when the nucleophile is sharing its electrons with the electrophile, it is the HOMO of the nucleophile is going to be sharing electrons with the LUMO of the electrophile. And so depending on the energies of the HOMO and LUMO, that's what's going to drive the reaction. So when we looked at the leaving group ability of our electrophiles, that impacts our LUMO. When we look at the nucleophilicity, how well something is a nucleophile, we're looking at the HOMO of our reaction. And so we can use our electrostatic, you've seen this image before, we can use electrostatic maps to kind of map those things out. So for example, if you have methanol here, there's a lone pair on methanol. This was actually in one of your classworks before, as well as this was on one of your other sheets. That lone pair can attack your electrophilic carbon, which is the methyl there, and kick out your leaving group in a substitution. And if we want to know which electrophile and which nucleophile would be best, we can actually calculate values of HOMO and LUMO and figure that out. And so we can do this calculation and we can see whenever the energy gap between the HOMO of the nucleophile and the LUMO of the electrophile are close enough, they're going to be easy to react. And so we'll revisit this idea later on. This is important in organic too. This is not something I'm going to test you on in your next test, but it's something to be aware of, that we can manipulate molecules to make them better. So these are some standard nucleophiles that you saw last time and some standard leaving groups, and we saw that iodide was a pretty good leaving group compared to the rest, and negative charges are pretty good electrophiles. And so when you do the energy gap between them, they are the smallest, so they are going to be the most reactive with each other.